we're probably ready to record. So,
Yeah.
so thank you for being here and for giving this talk. And please go ahead.
Thanks, Alec. Thanks for tuning in, whoever is on YouTube, or whoever is live. Thanks for tuning in for this talk, and also thanks for the opportunity to present at this reunion. I'm going to talk about this work, Price of Active Security in Multiparty Computation. It's actually a confluence of a few works in the last couple of years, joint with these wonderful co-authors. This talk is about secure multi-party computation. As all of you know, MPC allows a group of mutually distrustful parties to jointly compute a function over their private inputs where nothing but the output is revealed. MPC comes in many flavors. You can ask about adversaries that passively or actively corrupt parties. Passive corruption means the adversary corrupts the party, follows the protocol, but tries to learn more than it should. Active corruption, or what I would say full security, is when an adversary can corrupt a party and act arbitrarily, Byzantine. A second classification is based on the number of parties corrupted. There are two distinct settings here based on techniques and so forth. One is honest majority, where the adversary is only allowed to corrupt a minority of the parties. And the second setting is where the adversary can corrupt all but one. I'm going to focus on one result for the most of the talk, and it's going to be for the setting of getting active corruption, tolerating active adversaries that can corrupt all but one parties. MPC design typically follows these two steps. You first build a protocol that withstands a passive adversary, and then you amplify it to full security or withstand Byzantine adversaries. This talk is about what is the overhead of going from passive to active. In the past decade, we have seen like several tremendous improvements in passive protocols. Like now they're pretty efficient. We are looking at so many protocols for even neural network computations. But the overhead of moving from passive to active still seems a bottleneck. I want to say the state of the art is that when you want to move from passive to active, there is a blow up of order S, where S is the statistical security parameter. And I'm kind of focusing on the concretely efficient constructions when I say this. In practice, also, when you see the passive to active overhead, this is like between 20 to 100x, and it doesn't scale well also in terms of number of parties. In this talk, I'm going to talk about how to make this overhead a constant, and with also concrete efficiency in mind. And we're going to show for certain cases, it can be made close to 2. As I said, again, I'm focusing on concretely efficient constructions. If you want, in theory, you can get constant communication overhead. So what's the state of the art? First, in theory, why can you get constant communication overhead? Well, you take an arbitrary passive protocol, you can apply the classic GMW paradigm of attaching zero-knowledge proofs. And even better, if you use a succinct zero-knowledge argument or a snark, then to get an active protocol, you simply have to, for example, commit to your input and randomness, and then attach a zero-knowledge proof to every message. I'm simplifying here, but this is essentially what the GMW paradigm tells us. And if these proofs are short, the overhead of getting active security in terms of communication is quite small. It's in fact less than 2 if the zero-knowledge is small enough. But in practice, the passive protocol, the way they amplify it to get active is using this paradigm, which is cut and choose. And most practical constructions use this form of cut and choose one way or the other. Now, I want to talk about where you get this order S overhead. Roughly speaking, in all these works, what you do is you consider a slightly modified version of the passive protocol and run it n times. Now, the reason you want to run it n times is because each party is now going to check the other party on how it behaved in some of these copies. In other words, we're going to open your inputs and randomness for some of these executions and see if you behaved properly. Now, say Alice is going to check Bob on T copies. Now, if you set T appropriately just by a simple Chernoff bond, you can argue that if Bob passes this test, then for most of these executions of this modified passive protocol, Bob must have behaved honestly. And then you apply some clever kind of combiner to get your result. Now, the main point here is that if you want a statistical security of 2 to the minus s, you need at least s copies. And this is where the order s overhead comes from. So what I want to talk about is how do I make this overhead a constant? But even defining this problem is a little hard because in theory you can make it a constant. So what do I mean by making this overhead constant? So to do this, what we're going to do is we are going to define a primitive based on which we'll be able to analyze this metric. So I'm going to talk quickly. Everyone knows what secret sharing is. In additive secret sharing, you can share a secret between two parties where neither individual can identify X beyond 1 over F probability, where F is the field size over which this is being secret shared. Now, for such a secret sharing scheme, if you want to, MPC protocols are based on this. If you want to do a secure addition on shares, this is easy. If I have an additive secret sharing scheme, I can locally add and I can get secret sharing of the result of this addition. Now, multiplication, in other words, addition is free. You can do this locally if you choose an additive secret sharing scheme. But if you want multiplication, on the other hand, which is the same thing, I have secret shares of two secrets A and B, and I want to get secret shares of the product. This, on the other hand, requires communication. Okay, so I just want to quickly tell you the classic GMW protocol for securely computing any function in the passive setting. It works as follows. Alice and Bob additively secret share their inputs to each other, and then they do a gate by gate evaluation where addition gates can be locally evaluated, as I just mentioned, and for multiplication gates you use some protocol to do a secure multiplication. So you just keep doing it for all the multiplication gates. The addition gates, you do it locally, and then finally you broadcast the secret shares of the output. This is the classic GMW protocol, and in fact, this secure multiplication that you need needs to be only passively secure, because I'm only talking about a passively secure protocol. And if you look at the complexity of this protocol in terms of secure multiplication, I need one call to a secure multiplication gadget per multiplication gate of the circuit, or you can think of it per AND gate of the circuit for Boolean computations. So the reason I presented this is to say that the main question we are going to ask over here, to frame our question of getting a good overhead, we're going to ask, what is the overhead of achieving active security given only black box access to a passive implementation of secure multiplication? And the reason we're going to say black box access, because this is more efficient in practice. If you don't use the code of the protocol you're using for secure multiplication, in other words, like tailor-made zero knowledge proofs, then your construction is going to be more efficient. So restricting black box access to such a gadget, we're going to ask, what is the overhead of getting active security? And as we just saw before, if I just wanted passive security, I just need one call per multiplication gate. So the state of the art, when I restrict a question to this model, is something like this. And for the Boolean and arithmetic computation in the two-party setting, it's constant. But for arbitrary parties, there is still this order S overhead. And what we do in this work is we show that we can make this a constant. And I mentioned that this is for the dishonest majority setting with active security. Our framework is general enough that it can also capture and provide the same result for the honest majority setting as well. So the main theorem that we show, this is from the Eurocrypt paper this year, is we show that we can construct an actively secure multi-party computation for arbitrary functions over some finite field, making only constant invocations of a passive implementation of secure multiplication protocol per multiplication gate of the circuit. And this, in fact, like in practice, we implemented this for the two-party setting, and I'll show you some graphs. We can show that, we get roughly 2 for large finite fields.
I have a question, sorry.
Yes.
Is there any other communication beyond whatever is implied by calling the secure mall
Yes.
in the protocol? And is that dominated by the one that is in the theorem, or?
Yes, that's right. I mean, there are like smaller like additive terms that would come in the. I mean, it will be dominated by the passive protocol for secure multiplication. That's right.
Thanks.
Okay, so in terms of techniques, the main technique that we follow is this paradigm introduced by Ishai Prabhakaran and Sahai called the IPS paradigm. So here you want to, I mean, when you want to construct an actively secure protocol with dishonest majority, you can compose in fact in a nice I want to say even kind of black boxish way of two different kinds of protocols with different guarantees. So you can combine an active MPC with in the honest majority setting with a passive MPC with the dishonest majority setting. You can combine these two ingredients to get an active MPC with dishonest majority. Now, these are milder building blocks. In fact, we have very good protocols for both these settings. The passive, you just saw it. You can just think of the classic GMW protocol. And for this, there are very nice protocols to get active MPC in the honest majority setting. And just following, I mean, I won't use it too much. We call, the honest majority the outer protocol and the dishonest majority as the inner protocol. So what I'm going to do quickly is I'm going to go over this paradigm and then tell like where what we do in our work. So what is active MPC with an honest majority? The way we can think of this is you have clients that secret share their inputs to servers, and an adversary can actively corrupt all but one of the clients and can corrupt at most half of the servers. Okay, so this is the first ingredient that we want. And such a computation typically proceeds as follows. Alice and Bob secret share their input to the servers do the computation, and then they provide the answer back to Alice and Bob. Okay, the second ingredient is passive MPC with dishonest majority. Again, I'm showing it in the two-party setting. Whatever I'm saying also makes sense in the multi-party setting. So this is a passive protocol in the dishonest majority setting. An adversary can passively corrupt at most one client. Okay, so how do we combine these two ingredients? The basic idea is, I mean, in the real world, you only have the clients. These are the participants that you want with dishonest majority. Now, the first ingredient involves servers, but these are really not there. Now, the way you're going to do this is we're going to use the outer protocol, which is the honest majority setting, to actually compute the function that you care about. Okay, so this is going to do the computation. The inner protocol is actually going to be used to emulate these servers that only exist virtually or in the parties' heads. So you can imagine that each of these servers, the actions executed by each of these servers are actually going to be done via a passive inner protocol. Okay, so as such, when they are executing this protocol, neither Alice or Bob actually knows any of these servers unless they cheat in the passive inner protocol. If they don't cheat, then actually they can compute this function and this would be secure. But the point is, this is only the inner protocol is only passively secure, which means Alice or Bob can cheat, and by cheating they can violate the privacy of the outer protocol. So in order to make this thing work, a key idea in this IPS paradigm is the notion of a watch list, where Alice watches Bob on Bob's action on a few of these servers, and Bob watches Alice on a few of these servers. And what happens is that if Bob cheats in too many, then it's going to be caught. And if Alice cheats in too many, Bob is going to catch Alice. And in a nutshell, what happens is that by setting K appropriately, you can make sure that neither Alice nor Bob can cheat in the virtual emulation of these servers in, at most, a minority of these servers. So now the security of the outer protocol kicks in because this is actively secured, even if a minority of these servers were bad, we get the result of the computation will be correct and private. This is the IPS paradigm in a nutshell. And the key idea here is, of course, combining the outer protocol with the inner protocol, but using the watch list to enforce the requirements of the outer protocol. So talking about the efficiency of the IPS paradigm, imagine we have n clients, we have m servers and k watch lists. The efficiency of the system is roughly m by k. If you use a good outer protocol, which has using like pack secret sharing and so forth, you can get the efficiency to be m by k. Now, k, you should think of the watch list, you should think of it as the corruption threshold of, roughly the corruption threshold of the outer protocol. So you can construct good ones where m by k is actually a constant. This is easy. Now, to get 2 to the, it should be minus, but if you want to get 2 to the minus s soundness error, you need at least the number of servers needs to be at least the security parameter. Now, again, you can ask, now am I going to have the same issue as the classic, the cut and choose paradigm? The answer is no, because this computation is amortized. It's okay if the number of servers is a lot. But the second constraint here is the one that's actually a little more tricky. Now, if you have, I showed the diagram for 2 parties, but if you had many, many parties, each party needs an individual watch list that none of the others know. Okay, so, but if n-1 of the parties collude, then n-1 of the parties can watch n-1 times k of the servers. Now, this is the total number of servers they can watch. This needs to be less than the corruption threshold of the outer protocol, which means n-1 times k should be less than m by 2. And what happens because of this is that your the IPS paradigm in the multi-party setting, for constant number of parties, it works. You get like good constant overhead. And this is what I mentioned at the beginning. But when you think of arbitrary parties, there is, you will suffer an additional overhead of number of clients in the complexity. So the IPS paradigm is great, but it doesn't work for beyond constant number of parties. Okay, so this is where our work begins. And our approach is not to have individual watch lists, but actually to have a global watch list. Now, this doesn't make sense. It's not like everyone will be watching all the time a set of these servers, but at the end of the day, there will only be a single subset of servers that need to be watched. And the idea is you don't, like in the IPS paradigm, you can check if the other party is cheating or not during the computation, because you will have complete view of these servers. You can check during the computation if something's going wrong. But when we move to global watch list, actually, we can't do this, because if everyone knew which server I am watching, they'll make sure they won't cheat there. So, that's not going to work. So the set of servers that they're going to, check has to be revealed at the end. And also the correctness needs to be checked at the end. Okay, so this is our first key insight into making this IPS paradigm for arbitrary number of parties. So what's the challenge? The adversary, of course, now, as I said, it can violate the privacy of the inner protocol. This it can always do because it's only passively secure. Now, by violating the inner protocol, you violate the privacy of the outer protocol. Now, if you're checking things at the end, this is going to be a problem, because during the computation, if all privacy is gone, I've already learned your input. I don't even need to wait till the end of the computation. And sorry, right. So how do we solve this? So our next idea here is that we're going to choose an inner protocol that is weakly private. It is not, again, this is just, I'm oversimplifying the idea. Finally, we need only a passively secure inner protocol. But the way we instantiate our inner protocol, it will be weakly private, okay? Which means that during the protocol, the adversary cannot violate privacy. It can, of course, violate correctness. And then you make a tailor-made outer protocol where this privacy carries forward. So in other words, these two ingredients, what happens is that during the protocol, even if the adversary cheats in all executions of all the servers, it will not violate the privacy of the honest party's inputs. And then finally, you check the correctness for a subset of the servers before revealing the output. And this kind of solves the problem. And I should say, I'm not going to go more details into how this works, but it is the main technical contribution is how to make this outer protocol that preserves privacy. Okay, so here's just a quick graph on for the two-party setting. We didn't implement it yet for the multi-party setting. You can see the bottom lines here is just for the passive protocol. And then the next line here is our implementation of the active protocol. And this is communication and this is time. And this is the best previous protocol due to Overdrive, Keller et al. And we start with roughly like 4x overhead, and as we increase the circuit size, this tends to 2. Now, just want to say that there is also another metric that if you want to know, you can ask how many times do we call the secure multiplication. This doesn't quite show it because this is the end-to-end communication of our protocol. But there's a table in the graph in our paper if you want to see. As we go at close to I think 500,000 gates, if your circuit has 500,000 gates, then the number of times I have to call the passive implementation of a secure multiplication is close to a 2 for large fields. Okay, how much time?
This logware line, does it represent a protocol with what overhead asymptotically?
Which one? The Logier?
Oh, sorry, Logier, not logware, Logier.
So they use tailor-made zero-knowledge proof. So I can't quite tell what the asymptotic complexity is.
Okay, fine, thanks.
And a similar, you can see for the runtime of the passive versus active. How much time do I have, Ali?
You're doing good. You have 15 minutes.
Okay, great. I think I might finish faster. But anyway, so let me. So the main theorem that we show is that exists an actively secure multi-party computation that makes constant invocations of any passive implementation of a secure multiplication protocol. And the number of invocations is constant per multiplication gate of the circuit. I want to say that this outer and inner, the way I described was the inner protocol as a passive dishonest majority. If you replace it with a passive honest majority, you can also get a final protocol for the honest majority setting. And I want to say that one of the results that we improve here is for the Boolean setting. We didn't know before a passive to active with constant overhead. And as I mentioned, it's in practice, you can get this the overhead to be 2 for large finite fields. We implemented it for two parties, and we've not implemented it yet for multi-parties, but I'm going to tell you something more about the multi-party setting. So a couple of questions from from this work is that, what about concrete efficiency in the Boolean setting? So I've been telling that we get in practice 2 for large finite fields, but what happens for the Boolean setting or small fields? And we do get the main theorem holds, but it's not concretely efficient. And the main reason is we have to rely on algebraic geometric codes. We need secret sharing where the size of each share is also small. So, and these are at least not yet proven to be efficient in practice. Another question that we're going to ask is, can we get less than 2 and also concretely efficient?
Sorry, question. The AG codes, do you use them for their multiplication property?
Yes.
Okay.
So we're going to answer this a couple of these questions in specific settings, and we're going to say that we have to relax this black box condition that we have and give into some of these snarks, and also go closer to the GMW paradigm itself. So we're going to show that in some of these settings we can actually get something that's concretely efficient by following the GMW paradigm itself, and that's what I'm going to talk about next. So This is a recent work from CCS this year. It's about getting Boolean two-party computation. Now, we know the classic protocol for the passive setting for Boolean circuits. It's Yau's protocol. And here's just a small picture of how this works. You have a garbler, you have an evaluator. The garbler garbles the secret, the circuit, and also the inputs in a special form. And then it transmits, the garbled circuit and the garbled inputs to the evaluator. Its own inputs, it can send it directly, but evaluators' inputs have to be received via an oblivious transfer. Uh, so this is kind of the best protocol, and in fact, this is uh, again, we have seen a lot of improvement in the last decade of implementing this. We can do like billion gates secure computation with Yau's protocol. So how do we get active security here? Essentially, we're going to follow the GMW paradigm. We're going to say, let's attach a zero knowledge proof. Okay. Now, we're going to have a zero knowledge proof that goes from the garbler to the evaluator. Now, GMW paradigm requires, zero knowledge proofs both ways, like to show both actions are, both of them act correctly. But the nice thing of the Yau's protocol is if the oblivious transfer is in fact malicious or actively secure, then the evaluator can't cheat. It is already secure against an active corruption of an evaluator. So the only thing you want to protect is an active corruption of the garbler. So, the garbler proves that it constructed the garbled circuit correctly, it garbled its own input correctly, and it provided the evaluator's input in the oblivious transfer correctly. So this zero knowledge proof essentially needs to prove these three statements. Now, in our implementation, actually, we were careful about applying this GMW paradigm. And by that, I mean, this NP statement that we pick to prove over here is in fact will be black box in the oblivious transfer input outputs, but non-black box only in the pseudo-random generator. So we are relaxing our requirement of being black box, but we're being selective about it. We are only saying that, look, the PRG that's used to build the garble circuit will be non-black box in it in the zero knowledge proof, but be black box in the oblivious transfer. So how do we do this? So we extend this oblivious transfer functionality to a slightly more general functionality that we call certified oblivious transfer. And I'm going to tell you what this is. So in a certified oblivious transfer, and here is a parallel version of certified oblivious transfer. You want to do many oblivious transfers in parallel. If you recall in the Yau's protocol, you could do all of the evaluator's input in parallel. So the certified oblivious transfer is parameterized by an NP relation R that performs the following functionality. It delivers the input of the oblivious transfers to the receiver only if this relation holds with respect to some public statement X that both the sender and receiver know, and some private witness that the sender holds, and the inputs of the sender. Okay, so the certified oblivious transfer says that, look, I can apply an NP relation black box on the inputs outputs of the oblivious transfer and some other public statement. And this is exactly what we need in the Yau's protocol. So what is the point of abstracting this functionality is that we show how to implement this certified oblivious transfer with black box access to oblivious transfer and a commit and prove zero knowledge. And we're black box in the commitment as well, but we can use these two in a black box way to implement the certified oblivious transfer. I won't give this protocol, but this is kind of the main technical novelty, and we implemented this. The high level takeaway from doing this this work was that we could, this is feasible. Like with the current improvements in zero knowledge, this is possible, and we get our communication is smaller than twice the size of the passive protocol, and we don't even need to go for very large circuits. Even for moderately big circuits, we can show that the zero knowledge proof we have to attach is smaller than the entire protocol itself, which means the overhead is less than 2. Our implementation, however, we couldn't go more than I think we couldn't go more than I want to say, 1 million gates. And this is basically because the zero knowledge proof we were not careful about the memory usage. So we need a more memory efficient zero knowledge to actually make this work. Otherwise, your memory is going to blow up. But uh, the second thing is time. Now, the time taken to generate these proofs is also significant, but there is a nice feature that can be done in this work, which is that you can actually prepare most of your proofs ahead of time. In fact, you can prove that your garbled circuit is correct ahead of time. You don't even have to interact. It is not like normally when people talk about an offline phase. This is like a non-interactive phase where even before I know who I am talking to, I can build my garbled circuit with a proof. And you can also think even more where I can publish this on my web page, and it can be even publicly verified. So in our work, we also show here how this gives a nice non-interactive secure computation in this framework, where in the offline phase, where you can think of these garbled circuits being published and the receiver publishing its OT first message, and then in the online phase, there is a single message that goes from the sender to the receiver. In fact, this is what we implemented.
I have a question, sorry.
Yes.
Are in any of those works, do you also study the case of multiple parties, or?
So this was only for 2 parties. Yeah. So, I mean, this is specific to the YAO protocol. Right. But you're asking multiple parties? Sorry, go ahead.
Yeah, no, and yes, garbled circuits are specific to the two-party case, but are there some, I don't know, similar things that were, I don't know, having a black box access to OT and as a commit improves decay functionality helps you with multiple parties?
You can do this. I don't know how efficient it will be, but you can extend, like you can ask, right? I mean, the GMW paradigm can be implemented with oblivious transfer. Can you amplify it with active security using commit and prove? Yes, you can. Like, will it be faster than previous approaches? This is yet to, but you can. Like, I think communication-wise, it will be still good. Right. You can extend the certified oblivious transfer for many invocations.
Thanks.
But anyways, I'm going to answer another part of your question, scaling to very large number of parties. And again, I'm not going to do the Boolean setting, but I'm going to take a very specific scenario here, and I'm only going to talk about a highlight of the result that we did. So here is a specific task that you want to do using secure multi-party computation, which is distributed generation of an RSA modulus where no one knows the factorization. You can envision this as a multi-party computation where everyone has shares of the primes. They compute the product and check that it's a biprime. And this has gained a lot of attention, at least the past couple of years. Its implication to zero knowledge, its implication to, more importantly, verifiable delay functions. So what's distributed sampling of an RSA modulus? You have parties interact to jointly sample this N. Each party holds like shares of 2 numbers, P and Q, and they're going to multiply it, check if they are prime, multiply it to get a modulus. And I'm going to talk about the scenario where all but one can be corrupted. Okay, so this is our setting. We want to do distributed sampling of an RSA modulus. And we, in fact, are. This is another work of ours. This is going to appear in IEEE in Oakland next year. So we follow the GMW paradigm, but with a slight difference here. So we take a classic passive protocol for doing the distributed generation of RSA modulus. Now, as I mentioned, this is how the GMW paradigm works. You commit to your inputs and then attach a zero knowledge proof. But in the case of RSA modulus generation, there aren't quite inputs. There is only randomness. You're only sampling a modulus. So in fact, what we can do is we can move all the zero knowledge to just one big fat zero knowledge at the end. We don't need to do it at every step because there is no privacy that will be lost during the protocol. Because if it's going to be caught here, you can just restart the computation. So just want to tell you what our results here are. So, this was the best work before this appeared by Fredrickson et al. In Crypto 18. They generated a 2048-bit modulus with passive security, 2 parties. They used 8 GB RAM, 8 core, 40 gigabit per second bandwidth, per party communication 2 GB, and end-to-end time 35 seconds. So what we do is we were able to run a protocol for 1,000 parties. And in the passive setting, and each party, the spec that we have is like 2 gigabytes RAM and 1 core. I should, and very nominal bandwidth, 1 megabit per second, per party communication around 150 megabytes, and the end-to-end time was about 4 minutes. I should tell you that this is a slightly different setting than this in just one aspect, in that we wanted the party spec to be really, really small, lightweight. Like we wanted to, imagine this to be, if you want to run it on a browser or so forth. We involve a coordinator that coordinates the actions. Now, this coordinator doesn't come in the trust, because you don't have to trust the coordinator, because the zero knowledge proofs and the transcript finally will, even if the coordinator cheats, it will be caught. And the only thing the coordinator does is like public operations. So when you use like the secure, to implement secure multiplication in such a large scenario, you use threshold additively homomorphic encryption. And the operation that comes again and again is like aggregation. You have to add ciphertext, you have to add values. And these are public operations that we involve like a trusted coordinator, not a trusted, sorry, an untrusted coordinator to do. And what I'm hiding here in this line is that I'm not giving you the spec of the coordinator. I mean, you can throw whatever hardware you want on the coordinator, because you don't need to trust it. And we actually used the best machine on AWS for the coordinator. But we also implemented in the active setting, and for the 1,000 parties, the zero knowledge proof is not that big. It's like about 50 megabytes, so it adds very little to the communication, and our runtime was about 22 minutes. I should tell you that we didn't stop here. We wanted to see how far we could go, so we actually ran the passive up to 10,000 parties and the active up to 4,000 parties, and it kind of scaled okay. Like the end-to-end time was like 37 minutes for passive and 80 minutes for the active. I should tell you that these numbers, in fact, can be improved if you improve the coordinator. In fact, we use the best machine on AWS, but if we had more threads on the coordinator, this would have improved. The point I want to make is actually that the parties communication here, per party communication actually depends only logarithmically on the number of parties. Like it scales really, really, really well. And the computation of the party doesn't change even as you scale the number of parties, because you're only the computation is like sampling an RSA modulus. The circuit size doesn't change with the number of parties. So the per party computation and communication really scales very well. And the only reason this blow up in time is because we didn't get a better coordinator like machine on AWS.
What is the round complexity?
So it's 12.
So each party has to make 12 actions to report.
Yes.
So, I mean, for such large number of parties, how would one handle aborts?
So this is dishonest majority. So, you're not going to get guaranteed output delivery. You have to restart. So we introduced a kick out mechanism, which is like we waited for a minute. If not, we restarted the computation.
Okay, so the way to think about this, like this particular type of large scale MPC, is that somehow the parties are not bandits off the internet, but they're like somewhat lightly privated, so that you cannot have this denial of service attack where at every retry one party decides to cause an abort.
No, I mean, this is definitely vulnerable to that, right? Like if like every round some party can say, okay, I'm going to go home and like stop the computation. You need some external mechanism to prevent denial of service. I'll also just say one point here, which is that when I say the active protocol is 80 minutes, we are waiting for all the zero knowledge proofs to be transmitted and verified. Now you can imagine that you can do this optimistically. Like you can ask how long do the parties have to remain online, and that's only the passive, because you execute the passive and then you generate the proof. So at least in the 1,000 party setting, this is quite meaningful. Like you just need all the parties to be online for 4 minutes, and then later just upload into S3 or Dropbox your proof and verify it later. How much time do I have?
I think if you can wrap up in the next couple of minutes, that would be great.
Yes, I can do it in the next couple of minutes. Exactly. That's good. So the last thing I'm going to ask, okay, so we got overhead 2, then we asked about less than 2, and for the gobble circuit and for this RSA modulus generation, we did get less than 2. It is like passive protocol plus a snark. But now, can we do smaller than 1? And yeah, the question itself sounds ridiculous, but I'm going to like give some credence to this. So this is in one of our works. So we kind of try to leverage the leakage resilient properties of Reed-Solomon codes. And this is what we use, at least in the first work that I presented, like the outer protocol uses Reed-Solomon codes for essentially for packet secret sharing. So in standard secret sharing, the adversary receives T shares. In a leakage resilient setting, you have that the adversary receives T full shares, but also receives small leakage in the remaining N minus T shares. And this was kind of the first work that analyzed this setting. There has been a lot more work that I've not listed over here that as like this is a very active research area of getting leakage resilient secret sharing. So what we do, at least we proposed this in our work, and this was in CCS last year, where instead of starting from a passive protocol and amplifying it to active, start with the leaky protocol and amplify it to active. And this actually makes sense when this secure multiplication primitive gadget that I said, when you implement it using like lattice-based constructions, if you make these parameters actually aggressive, it is leaky. And by leveraging the leakage resilience of Reed-Solomon codes, the transformation that I mentioned, which is going from like using the outer and inner protocol, you can take it from leaky to active. And we proposed a way in which this can be done. There's still a gap between what kind of leakage resilience is provided by the scheme and what we need. Like there's still a gap which we are currently working on, but we did propose an idea where we could go from leaky to active using the same compiler. And this has overhead 1 in the sense that if you look at the current best passive protocol based on these lattice encryptions, if you start with something leaky and go to active, you could get better than that passive. So I am cheating in saying it's less than 1, but this is kind of what we get. We could go even better by starting with a weaker primitive. And there's some other works that I'm currently involved where we can show that this also has some connections to getting like zero knowledge PCP. Okay, so this is my last slide. So the first result I mentioned was a general framework of moving from passive to active with constant overhead. It works for Boolean and arithmetic. Any number of parties, works both honest majority, dishonest majority, and uses the secure multiplication gadget in a black box way. If you relax this black box requirement, then you can get overhead less than 2 by applying like a variant of the GMW paradigm. We showed this for the Boolean case in the 2-party setting with gobble circuits, and also this distributed RSA generation where we could scale it really to a large number of parties. And finally, like if you want to push it even more, reduce this communication, start with the leaky implementation instead of passive. Most of this work, all of this works that these works that I've talked about, I've only focused on the communication overhead. I should tell you that, okay, now we have a good idea of getting a good overheads for communication complexity, but computational complexity is still, there are many open questions, both theoretic, like even the asymptotic setting is not yet resolved. And in fact, right now in the special case of zero knowledge, we are seeing many constructions where you have like linear time provers, but in the MPC setting, like many of these questions are still open. Thank you.
Great. Thank you, Muthu. I think it was right on time. Perfect. I think I've asked all my questions during the talk. I don't know if Stefan is there, has any questions for Muthu. All right.
No questions.
Okay. Sorry to hold you on. Okay. Thank you so much, Muthu. So I think we're done for the day here, and there's another 4 talks tomorrow, 2 in the morning, 2 in the afternoon.
Yeah.
Take care, everybody. Bye bye.
Thanks. Bye.